today we will be discussing about the equivalent circuit of the synchronous generators and its terminal voltage for different types of the load. In the last lecture, we have studied about the different types of the voltage drops in the generator, and now we'll discuss, or we'll try to correlate with the equivalent circuit, and we'll try to again redraw the phasor diagrams. So the topics to be covered today are the equivalent circuit, the synchronous reactance, phasor diagram, and no load terminal voltage for different loads. Now, equivalent circuit of an alternator. Now, last time we had discussed this, that is, R is the resistance of the given machine, that is the synchronous generator, XL is the leakage reactance, and XA is the armature reactance, armature reaction reactance, and you can combine this XL leakage reactance and the armature reaction reactance, which will be in total given as the synchronous reactance, that is XS. So the figure shows the equivalent circuit of the loaded alternator for single phase. Now all the alternators are normally three-phase synchronous generators, but whatever we discuss or whatever line diagram we make, that will be per phase, in per phase only. And if I say that the armature resistance is 0.1 ohms, this means I am talking about the armature resistance per phase. Okay, so every time we need not mention that, but actually whatever quantities are being mentioned, that is in the per phase quantity only, other than the total power or the total torque produced. So here E0 is the no load EMF produced by the synchronous generator, and E is the EMF induced on load. So E is the induced EMF after allowing the armature reaction also, and it will be equal to the phasor difference of E0 and IA XR that we have already done in the last lecture. So E0 will be equal to E plus IA into J XAR, because it will be in quadrature. The behavior of the armature reaction is the same as the leakage reactance. If V is the terminal voltage and the drop is given V is the terminal voltage, and it will be less than the induced EMF because of the voltage drops in the leakage reactance and the armature resistance. So E will be equal to V plus IA into RA plus JXL, and plus you can add the armature reactance also to get the final terminal voltage on load. Now this is the phasor diagram which you can see at the bottom. So now we can, because this leakage reactance as well as the armature reaction reactance, they both are inductances and the same current flows through both the reactances. So they can be assumed to be in series, and hence we can add the two quantities and make a single term which is known as the synchronous reactance. So the synchronous reactance is a fictitious reactance which has to take into account the voltage effects in the armature circuit produced by the actual armature leakage reactance and the change in the air gap flux caused by the armature reaction also. So over here we have combined the two, and the resistance plus the reactance will give you the synchronous impedance. So the synchronous impedance is given by ZS is equal to RA plus JXS, that magnitude will be whole under root RA square plus XS square, and when you take it in the form of the total impedance, and then you can write your E0 as E0 will be equal to V plus IA into ZS, and where ZS is equal to RA plus JXS, that is the synchronous reactance. So over here the phasor can be combined together, and you can have your terminal voltage by adding these drops to the E0 induced EMF at no load, and then you can calculate the actual terminal voltage at the output of the generator. Now phasor diagram for different types of the load. Now over here we will be combining all the loads. So first figure is for the your armature drop. The at unity power factor, armature current is in phase with the voltage, plus IRA drop will be in phase with the voltage, XL drop in quadrature, and the armature reaction drop will be also in quadrature, combined will be excess. So you will get the terminal voltage in terms of E0 and E. So over here, next figure is of the inductive load, where your current is lagging behind the voltage by an angle of phi, because for an inductive load the current lags the voltage, terminal voltage, and this is your again armature resistance drop in phase with the current. You can see the parallel line, and then in quadrature you will have the reactance drop, synchronous reactance drop as IXS, or you can divide it into two parts, the leakage reactance and the armature reaction drop, and you will get the terminal voltage V. Similarly, for the capacitive load, the current will lead the voltage by an angle phi. So here is the current leading by an angle phi. So IRA drop again in phase to the current, and you will add the reactances drops or individual drop as the synchronous reactance, and you will get the terminal voltage V with the knowing the no load induced EMF in the armature. Now the no load terminal voltage is given as E0, and the armature, the no load expression for terminal voltage for resistive load is given by the no load terminal voltage E0 is the actual induced EMF in the armature produced by the main magnetic field IM. It is the vector sum of the terminal voltage at load, drop in the resistance plus drop in the synchronous reactance. So this is the final figure we get it. Here it is simpler because here we have not segregated the synchronous reactance, plus we have not considered the E. It's only the no load voltage and the actual voltage on load for resistive load, because current is in phase with the voltage. So you can have the from the right angle triangle as OC square is equal to OB square plus BC square. Substitute the terms. So it will be OB will be equal to V plus IRA drop, and BC is your reactance drop. So your E square will be equal to V plus IRA square plus IXS whole square, or you can write E is equal to whole under root of V plus IRA square plus IXS square. Similarly, for the inductive load, the current will be lagging the voltage by an angle phi. So again you can take the complete triangle as your V, and then you can see this component will be, because current is lagging the voltage by an angle phi, so IRA drop is also lagging the voltage by an angle cosine of the angle will be in phase of the voltage. So IRA drop cosine is in phase with the voltage, that will be added, and plus the IXS drop sine phi is in phase with the voltage, so both addition will give you the E0. So once you can consider this terminal voltage for inductive load as OC square will be equal to OD square plus DC square, then you have divided into two parts. OD will be divided as OE plus ED, where ED will be equal to your IRA drop, and your DC is divided into two parts, that is BD and BC, and then you can write as your dB is equal to your EA. So substitute the values. Your E square will be equal to V cos phi plus IRA square plus the sine components, that is the quadrature components, V sin phi plus IXS whole square. So taking whole under root will give you the value of the induced EMF, or in other terms you can calculate the terminal voltage by taking the square, expanding it, and neglecting the higher order terms. Just take the square terms and find out the total resultant. So that is the approximation we do to calculate the terminal voltage in terms of this phasor diagram. So for the capacitive load, the current will be leading the voltage by an angle phi. So again it has been resolved into different parts. So OC square will be equal to, because OC is the E is 0, and therefore it is equal to OD square plus CD square. You can just segregate into two parts and get the actual value, and therefore you will get E0 square is equal to V cos phi plus IERA drop. V is this part and this part is the IERA drop, because this is your IR drop, so this is the cosine of it, so that will be added to it. And in the quadrature component you have got this, so that is your V sin phi, and plus you have got the XS component. So this component in quadrature you will have the component as IXS. So when you square it, when you take the under root, you will get the value of the E0. The only difference between the lagging and the lagging load and the leading power factor load is that over here it was positive before for the lagging power factor loads, and for the leading power factor loads we have got this as negative. The remaining this X components remain the same, only the change is in the Y component because it is the leading power factor, so you will get this as the negative. Now approximate expressions, as I told you, what we do is we expand it, they take the square of the terms and the higher order terms are being neglected, and by taking the total square root you can approximate it as in terms of unity power factor, E0 will be equal to V plus IRA, and for inductive load it will be V plus IRA cos phi plus IXS sin phi, and for the capacitive load it will be given as V plus IRA cos phi minus IXS sin phi. So today we have considered the equivalent circuit of the alternator, the synchronous reactance by combining the leakage reactance and the armature reaction reactance, then the phasor diagram for the different types of load, and using that phasor diagram we have calculated the terminal voltage for different types of the load, and finally we did some approximation to get a simpler equation. So thank you.